Moving on into this chapter, we're going to start with density. So density is defined as mass over volume. In particular, the mass generally is measured in grams and the volume in milliliters or centimeters cubed. This is a good time to mention that milliliters and centimeters cubed are the same thing, so you can use them interchangeably. So if something asks for some volume in centimeters cubed, but you're given something in liters, then it should be an easy conversion from liters to milliliters or something like that. So very interchangeable. A nice way to remember this equation is that density equals love. We have mass over volume, which looks like an m over a v. So density equals love. So density is an intensive physical property, which means that it is independent of the amount of how much you have. Independent of amount. So it means like if I have a small piece of water, like a small cup of water, or a large jug of water, or like a lake, assuming it's pure water, then they're going to have the same densities. It doesn't matter how much you have. Density is kind of like an internal property. So intensive is kind of like internal. Extensive is opposite. It is dependent on the amount. And so that means that as we have a small amount or a large amount of stuff, then that property would change. So some physical properties that are extensive are mass and volume. So like for example, if I have a big amount of water or a small amount of water, the mass is different, the volume is different. So those are some examples. Some other examples of intensive would be like temperature, boiling point, these kinds of things that don't change if you have a different amount. So a lot of times density and mass get interchangeably used. When we think of something that's, floating, we think it has a small mass, but that doesn't necessarily matter. Density is the proportion of the mass to the volume. So something can have a similar mass, like we could have a big ball and a little ball. They could have the same amount of mass, but their densities are going to be different. So it's all in proportion to something else. So in this calculation, we have a man who got a ring, and we're told that it's made out of platinum. But before the wedding, he noticed it feels light, so he checks its density. He measures its mass, 3.15 grams, and finds the displacement to have 0.233. So basically what he did was he said, okay, here's a graduated cylinder, it has a certain volume, puts the ring in, plop, the volume changes, that is equal to 0.233 centimeters cubed or milliliters. So we need to know, is that ring made of platinum? So we have these density charts here where we can check check the density to the standards. So we can say, okay, we need to check the density. Density equals mass over volume. So we're going to put 3.15 grams over 0.233 centimeter cubed. So when we go in and solve for that, we get 13.5 grams per centimeter cubed. So let's look. 13.5 looks like something like mercury. Platinum is 21.4, so no, it is not platinum. Is it mercury? That is unlikely since mercury is a liquid at room temperature. So what it probably is an alloy of two different types of metal. So probably like, maybe it does have some platinum in it, but then it's kind of like diluted or mixed with something like copper to bring down the density and also probably bring down the cost. More problems like this. So that ring is fake, so we get a new ring and it displaces 0.212 centimeters cubed. So if it is actually platinum, how much should it weigh? So now we're going to plug in density equals mass over volume. In this case, we know the density of platinum is 21.4 grams per centimeter cubed. That equals, we're trying to find mass in this case, and then the volume is 0.212 centimeters cubed. So we can multiply that up. So we'll have 0.212 times 21.4, and the mass should weigh 4.54 grams if it is indeed platinum. In this problem, we have a cube that has a length of 11.4 millimeters. So we'll draw a little cube. And that side is 11.4 millimeters. It has a mass of 6.67 grams. So we want to find the density. And again, we're going to measure in grams per centimeter cubed, or milliliter, same thing. So we want it to be in grams per centimeter cubed. So you could either convert this to centimeters now and then cube that, or cube this millimeters and then convert it to centimeters. I would prefer to do the first. So we're going to convert those millimeters. We know that there are 10 millimeters in a centimeter. And if you remember what a ruler looks like, you have those centimeters that are one of the last written digits, and then you have the markings in between. Those are the millimeters. So we do know that there are 10 millimeters in 1 centimeter, but so you might be able to do this one in your head, that conversion, but if not, that's okay. 1.14 centimeters. So now what we're going to do for the volume is we're going to cube that guy. It's the length cubed, so we're going to cube it. So the volume of this is 1.48154 centimeters cubed. Now, would I write all the digits? For now, yes, that's not our final answer. And so notice it came with 3 sig figs, so we're going to just keep 3 sig figs in mind. But when I plug this into my calculation, I want to use the whole number so I don't get some rounding errors. So now we're going to do mass, which in this case is 6.67 grams per this volume down here. So divide by that. And what we get for the density is 4.50 grams per centimeter cubed. This is where we would round. So by reporting that 0, we know that it is significant. In this problem, we have 3 boxes. So first ones we're going to look at is the left versus the middle. And as a reminder, we have density equals mass over volume. So the left box, left, middle, right. Which is denser, the left or the middle? So we're looking at the left and the middle. Left, so they both have the same volume, okay, but it looks like the middle one has more particles in it. So, and since they're all identical, the mass should be more. So in this case, our middle box should be more dense because it has a larger amount of mass. So if we look at the left box and the right box, which one's more dense? So we have here same amount of particles, so the mass is the same, but the volume is different. So in this case we have mass over volume. When we have a larger volume, our density decreases because we're dividing by a large number. So our denser one is the left box. So if we have a fourth box, same volume as the small guy over here on the left, but has 4 orange balls, is it true that this box, if they both have the same density? Well, it really depends on the mass of those orange particles. If they are the same as green, then yes. If they are different, then they would have different densities. The next section we're going to talk about is energy, and it is one of the last concepts we're going to learn in this chapter before we just do lots of different calculations of dimensional analysis. So when we have some kind of chemical or physical change, we are going to also have some kind of change in energy, either the gaining or releasing of energy. When we have energy, the definition is the capacity to do work. Now work is force applied over a distance. So work equals force times distance. So when we push a box, then we're applying a force to it. When we push it over a certain distance, that takes work. When we have some kind of force, that means that we have either a push or a pull on an object. When we have electrostatic force, that means that the objects have some kind of electrical charge. So the force is due to electrical charge. So in the case of this little kitty here with the balloon, cool, electrostatic force, but also we'll get electrostatic force when we deal with electrons and protons and elements, ions. We're going to deal with this one a lot. In the first law of thermodynamics, it says that the energy of the universe is conserved, which means that we're not going to be able to create any more energy or get rid of any energy. It just is transferred. All matter has some kind of energy, and that is in the form of either kinetic energy or potential energy, and each of those have subcategories that can be classified as either. So kinetic energy is associated with movement. This could be literally just moving. In that case, it's 1/2 mv squared, where v is velocity here. So that could be, driving a car, running. It could also be related to like thermal motion. So I'll say thermal energy, which when molecules are moving or vibrating. So that's all kinetic energy. Potential energy is associated with both position as well as composition. So whether we're dealing with a spring and we're putting some kind of pressure on a spring, it has a lot of stored energy in that way. Or being up high on a mountain or on the top of a building, lots of potential energy. No movement, but the potential for movement is high, right? It can be transferred into kinetic energy, and that's usually what happens. So this could be, the top of a mountain or top of a high place, we'll say. It could be the food you eat. Could be from a spring. Lots of options for potential energy. So like I was saying, energy can be converted. So one common one we do is we eat food, right? We have our food has calories. Those calories are a form of energy. So when we eat, our body breaks down the food, which has chemical energy in it, so that potential energy. And when those bonds get broken, energy is released through ATP, and then we use that as heat. Our body stays warm with food, or also movement and being able to just be active humans. When we're talking about energy conversion, we have to first define a few different things. So the system is the thing that we are studying. So in this case, it's this green box. The surroundings are everything around it. So what is surrounding the system. So this blue square. And the universe is the system plus the surroundings. So the whole scenario. Now, when we're talking about heat transfer or energy flow, we need to be thinking about where is the energy going. So if it's endothermic, then heat is transferring from the surroundings into the system. So the system is gaining energy and the surroundings are losing energy. With exothermic, the system is losing energy, so it's going from the system to the surroundings. So the energy of the system is going down and the surroundings going up. Now we measure energy change with temperature. So we can tell if something is gaining or losing energy by seeing what's happening with the temperature. So if the energy of the system goes up, then that means the temperature is going to go up and the surroundings are going to go down. So they're going to be proportional to each other. We measure energy in joules. That's the SI unit for that. Oftentimes in our daily life, we're dealing with calories, which is 4.18 joules is a little calorie. A kilojoule is 1,000 joules. A kilocalorie is the calorie we think of when we think of food, so it's a capital C, and that is 4,184 joules, or 4.184 kilojoules. And then a kilowatt hour is a common unit for energy when we're talking about like what we use in our homes. We'll hit up energy again in the end of the year, and more specifically in general chemistry too. We'll really have a big focus on it. We'll do a little bit throughout, but we'll really hit it up towards the winter time. But one thing that's way more important right now is dimensional analysis. So this is where we're using different relationships between different units to convert between another. So we can write those as equivalent statements. So it's like a definition, right? We talked about those with sig figs. So 1 inch is exactly 2.54 centimeters. We could write them as an equivalency statement. We could also write that as a ratio. So we can do 1 inch over 2.54 or flip it depending on where we're trying to go and what we start with. So let's practice. First thing you want to do is when you read the problem, you want to figure out what has been given and what you need to find. So specifically, if we want to end with one type of unit, so let's say grams, we want to find grams, and we start with, and they might tell you lots of different things, but let's say we're going to start with liters. So we need to be able to find, so that's what this next part is, find a relationship between them. So first we want to find what's the quantity and singular unit. So key thing here is this number should just have a single unit. It should not be per anything. It should just be 1 unit if we're going to end with 1 unit. That's where you start. That's where a lot of people get mixed up, is they want to start with some of those conversion factors, and we don't want to start with those. We want to start with just the single number with the single unit. Then when we find those relationships, those conversion factors, we can put those in between to help us get from one to the other. And density is actually one of those. That's why we talked about it. So we could use density as a conversion factor rather than using the mass over volume. And that's what I would prefer you do. Then we want to think about how do we get from our beginning step to our ending step. That might be looking up a conversion online. That could be reading the problem and seeing what they give us. But you want to start with the unit you have and figure out where can you go from there. What do they give you that can lead you to a new step? It might take you 5 steps to get out of it. It might take someone else 2. It doesn't matter as long as you all get there, and it should give you the same answer. Then you want to make sure your units are canceling out. So if I start with liters, my first step should cancel liters, and I should go into my next unit. And then that next unit should cancel and go on to the next one. So make sure your units are canceling. Then you're going to plug it into your calculator. Ideally, you type it into your calculator in one long step, multiplying numbers on the top, dividing by numbers on the denominator, and then getting one answer at the end. I really want you to practice this. And then make sure your answer makes sense. Double check it. If it seems wrong, go check your math. That's where it's like if you only did one string of answers, it should be really easy to check your work. So starting out, here we have it's like kind of a medium challenge one. We want to convert 1.76 yards to centimeters. So the first step is figure out what you have. We have 1.76 yards, and we want to go to centimeters. So we now need to find a path to get there. Now, this could be different for every single person, depending on what you have in your back pocket to get there. So when I think of yards, I immediately think of how many feet there are. So I know in 1 yard, there are 3 feet. Then going out of feet, I think, okay, well, the only thing I really know is feet to inches. So if in 1 foot, there are 12 inches. You might wonder, why did I put feet on bottom? Well, that's because I started with feet on top. Why did I put yards on bottom? Because I started with yards. So let your units guide you. Now I'm like, okay, I have inches. I want to get to centimeters. Do I have that relationship? Yes. So we're ultimately aiming for the end goal. If you make a couple steps in between there, That's okay. You'll ultimately maybe just have to put a couple more numbers in your calculator. So we solved that, and we got 160.934. So we'll round to 3 digits, and we'll have 161 centimeters. Here we have 288 centimeters. We want to go to yards, so we're going to do something similar. We're going to start with the number they give us with the single unit, and we're going to get to yards. So now we're basically just going in the opposite direction. So I have centimeters. I want to get into inches. So I have 2.54 centimeters in 1 inch. I have 12 inches in 1 foot. And I have 3 feet in 1 yard. So I'm going to type in 288, divide by 2.54, divide by 12, divide by 3. You don't even have to hit enter, and it will do it for you, and you should get 3.15 yards. In this next one, we're converting quarts into cubic centimeters. Now, I don't know about you, but I don't know many conversions that go from quarts to anything, so you can try to figure that. You can look it up, right? If it was an exam, I would give it to you, give you at least a conversion that would get you out of there. So, if I have 1.8 quarts, and I'm trying to get 2 cubic centimeters, so make sure you cube that guy because that's really important. So on our equation sheet and on the next problem, on the next slide, you can see that 1.057 quarts are in 1 liter. You might also find out that 1 quart is 0.95 liters, and that's fine. Where you put your numbers will just be a little different. You should get the same answer. Okay, so we need to go now from liters into centimeters cubed. But we know centimeter cubed is the same thing as a milliliter. So can I go from liters to milliliters? Yes. Now that's the thing that, that's why this relationship is so important, because sometimes it's easy to get stuck with centimeters cubed. And so we just remember, same as milliliter. So 1 liter is 1,000 milliliters, and 1 milliliter is 1 centimeter cubed. So just to be thorough and show you all the units canceling out, when we do that, we get an answer that is 1.7 times 10 to the 3rd centimeters cubed with 2 sig figs. If we want to go from centimeters cubed to gallons, we have 9255. We'll start there. Into gallons. Okay, so we can do a similar thing, but going backwards. Because I do know that we can find, well, I'll get there in a sec. So I know that 1 centimeter cubed is 1 milliliter, and there are 1,000 milliliters in a liter. So can I get from liters into gallons? Yes, you can if you look it up. I'm going to just go here to quarts. So I'm going to do 1.057 quarts in 1 liter from before, and I know that there are 4 quarts in 1 gallon, and I just know that from my daily life. Also, a quart means a quarter of a gallon, so just FYI. When you do that, you get 2.448 gallons. Okay, so for this one, we're going to do something very similar, but now we're going to do multiple steps because we're going to try to go from gallons of volume into mass, but we're going to use the density. So similar to what we did before, we're going to start with our number, 2.5 times 10 to the 4 gallons, and I want to get into milliliters, so that's cool. We don't have to go into cubic centimeters, that's nice. So we know, like last time, 1 gallon is 4 quarts, and there are 1.057 quarts in 1 liter, and we're just going to milliliters, so 1 liter is 1,000 milliliters. Now I'm doing it fast because I've done this a lot, and I can usually do it, but if you need to make a plan, that's fine. These are nicely given to you, so hopefully that helps you, but yeah. if you need to plan it out a little bit more, that's okay. And be okay with erasing. So this is 9.4607 times 10 to the 7 milliliters. Now, these two digits here are the significant ones. If I was going to stop here, then I would just write 9.5 times 10 to the 7th, but I'm going to keep going. So if the density is this, turn it into grams. So we're going to take this whole answer here, 9.4607 times 10 to the 7 milliliters. And now I can use the density. Now, did I have to stop up here to go into grams? No, but I want to just show you how this stuff works. So instead of plugging into density equals mass over volume, I can now use the density here to do the conversion. So I have, for density, it's 0.659 grams per milliliter. If I was in grams and I want to go 2 milliliters, I would just flip it, so I'd put the milliliters on top, and a 1 goes with the milliliter. So this answer is 6.2346 times 10 to the 7 grams, keeping in mind only 2 of the digits are significant. Now we're going to take that number and go into pounds using this conversion. So I have 6.2346 times 10 to the 7 grams, and I know that there are 453.6 grams per pound as said in this problem. So we're going to take that number and divide by 453.6, and we get 1.3744 times 10 to the 5th pounds. Or, remembering this is our end result, we would write 1.4 times 10 to the 5th pounds. So many steps, but this could be done in one problem if you're given this, these, and this bottom conversion. You can do it all in one string with 5 different parentheses. So for these problems, I would encourage you to try calculating them. You don't have to. You can try to use common sense or like your life experience if you want. So, and honestly, I think that is good. So keeping in mind that a kilometer is about half-ish a mile, which one's longer? So that means that about 1 mile is 2 kilometers. So if I run a 5-kilometer race, that would mean that is about half of that in miles, so about 2.5 kilometers. So a 5-mile race is longer than a 5-kilometer race. And then in this one, we know 1 pound is 450 grams-ish. So if we have a 5-pound box, that is going to be about this times 5. And 500 grams. Box is actually about a pound, so this one is more. Why can't you answer this question? So it says, if a forecast calls for sunshine and 35 degrees, what kind of clothing should you wear? So what's missing? We need to know what kind of degrees. Are we dealing with Fahrenheit? Because Fahrenheit could be, that would be very cold. It could be a sunny, freezing day in the winter, or it could be 35 Fahrenheit, which is pretty warm. It's up in the 90s, so, or for Celsius. So are you dealing with Fahrenheit or Celsius? Hard to say. That's why we cannot answer the question. So getting into some more conversions, these ones having to do with raising to a power. So keep in mind that when we convert between something, let's say we're going between x cubed and y cubed, and we only know the conversion between x and y. We don't know the cubed version. So let's say what we would need to do then is, let's say I have 3x is equal to 1y. I know we're getting into algebra stuff right now, so bear with me. So I don't know the cubed versions, but I do know just the uncubed relationship. So what I could do is write that down and then cube the whole thing. So that means I'll cube the every single part, including the units and the numbers. So that's what we do. Don't forget to cube everything, not just the thing you're wanting, the number, but the actual whole thing. So if we have 5.70 liters, I want to calculate that amount in cubic inches. So I want to go from 5.7 liters to inches cubed. So already people might be like, whoa, what's going on? But we know of a distance cubed, so in volume form, we know centimeters cubed, and we can get from centimeters to inches. So, and we know centimeters cubed to milliliters. So that should be kind of our hint. So we want to go to milliliters. So 1 liter, to cancel out that, is 1,000 milliliters. And now that nice little conversion between milliliters and centimeters cubed. Now we're in centimeters cubed. So do I know centimeter cubed to inch cubed? No. But do I know centimeters to inch? Yes. So I know from before that there are 2.54 centimeters in 1 inch. So that doesn't cancel out everything. I still have a centimeter cubed over a centimeter is a centimeter squared. So we can't just stop there. So what we're going to do is cube that whole thing, which means we're cubing 1, which is just 1, cubing inches, cubing that number, and cubing centimeters cubed. Now our centimeters cubes cancel out, and we are left with inches cubed. So very good. So we'll type in 5.70 times 1,000 times 1, and then divided by 2.54 raised to the 3rd power. So we just divide by that. When you do that, you get 347.8, which will round to 348 inches cubed. So trying to figure out how many cubic centimeters are in 2.11 yards cubed. So set yards to centimeters. We did this earlier. So very cool. We already did this. Yay. So we went from yards to centimeters. So before we cube anything, we'll say, okay, we know that in 1 yard, we have 3 feet. So cool, I can do that. Now I'm going to cube it. So 3 cubed, feet cubed, 1 cubed, yard cubed. Cool. Now I'm in feet cubed. Feet, we know that in 1 foot, there are 12 inches. So cube the whole thing, which means everybody gets cubed, including the 12. And then we're going to go from inches to centimeters. So 1 inch is 2.54 centimeters. And cube that whole guy. So cube everybody in there. So when we type this in, we'll do 2.11. Don't cube that. Just that's the number. Times 3 cubed. Times 12 cubed. Times 2.54 cubed. And the number you'll get is 1.61 times 10 to the 6th centimeter cubed. Cool. So not too tricky. You don't have to calculate that value. You just cube it and your calculator will do the whole thing. The last one here is we have a vineyard that has 145 acres of Chardonnay grapes. There's a soil supplement that requires 5.50 grams per every square meter of the vineyard. How many kilograms of the soil supplement do we need for the vineyard? And it tells us 1 kilometer squared is 247 acres. So what we can do, start with the number that has 1 unit. So this one has 2 units. It's a gram per meter squared. This one, the equivalency statement, 2 units. So we want this guy. So we're going to start with 145 acres. Then we find the thing that gets us out of acres, which happens to be this last little statement. So I want to get rid of acres. So 247 acres is 1 kilometer squared. So I'm in distance squared. So I need to find something that has a distance squared. Look. Oh, here it is right here. We have that soil supplement density or area that we need. So I need to get into meters squared. So I need to go from kilometers to meters. Well, I don't know that squared, but I do know that 1 kilometer is 10 or 1,000 meters. So I can cube. Nope, I lied. Wrong thing. I can square that. So I'll square everything in here. Square, square. And move on with my life. So now I'm done with squared kilometers, and I'm in meters squared. And now I can use that soil area, and I can say for every meter squared, they put down 5.50 grams. And then I want to find out how many kilograms. So I need to do 1,000 grams in 1 kilogram. So after doing 145 divided by 247 times 1,000 squared times 5.5 divided by 1,000, I get 3.23 times 10 to the third kilograms. So quite a bit. In this problem, we're going to now start using density as a conversion factor, so a little bit more intentionally. So we need to know the amount of fuel in a jet before you take off, so that way you can fly the right amount but not be too heavy. So we have 747 is fueled with 173 231 liters of fuel. The density is this. That's grams per, I'm just going to put milliliters because same thing. What's the mass in kilograms? So I want to know the kilograms of jet fuel. So this number, irrelevant. It's just a type of plane. The only number that has a single unit is the amount of fuel. So I'm going to start there. 173, 231 liters. So I need to get to kilograms. So volume to a mass. That involves density, volume, and mass. So my density is in grams per milliliter, so I'm going to get my volume into milliliters. So 1 liter is 1,000 milliliters. And now I'm in milliliters, so now I can use my density, 0.768 grams per milliliter. And I'm in grams. Cool. So now I'm in my mass. I can get into the right unit of kilograms. So 1,000 grams in 1 kilogram. So take your volume times 1,000 times the density divided by 1,000, and we get 1.33 times 10 to the 5th kilograms. Cool. So backpackers use white gas fuel for cooking stoves. If one canister contains 1.45 liters of gas, the density is that number. What's the mass in kilograms? So similar thing. This is in same thing as milliliters, so I'm just going to write that down because that will make it a little more straightforward. 1.45 liters. I want to get into kilograms. Literally same thing, new density. So 1 liter is 1,000 milliliters. Now my density is different, so I have 0.710 grams per milliliter. And then I want to get into kilograms, so I'll take 1,000 grams per kilogram. When we solve for that, we're going to get 1.03 kilograms. Okay, last one of this type. If we have a drop of gasoline, has a mass of 22 milligrams, and here's the density. So you might think, hey, I can just convert this to grams and then plug it into my density equals mass over volume. Totally, you really could. That's fine. You can do that. Like I said many times now in class, it's just a little bit more straightforward to do it this way, and then you don't have to remember the equation and how you manipulate it. You just plug it in and use the units to either multiply or divide. So we're going to start with our 22 milligrams. And plus, you already have to do a conversion, so it's like, whatever, you know? Okay, there's my single unit. I don't want to use this guy start with that guy because it's 2. So milligrams, we need to get into cubic centimeters somehow. So we need to use our density to go from our mass to our volume. So we have 1,000 milligrams in 1 gram. Now you might be wondering, do you have to know those? Yes, so get on it. You need to be working on those prefixes. Be working them a lot. Like this is hopefully helping with that. So 1,000 milligrams in a gram. And now I'm in grams, so I could use my density, 0.754 grams per centimeter cubed. Now, notice my grams are on bottom, so I'm dividing by my density here. So that's how that works out. Now I'm in centimeters cubed. Done. So my answer is 2.9 times 10 to the negative 2 centimeter cubed, or 0.029 centimeter cubed. Same thing. This is a challenge problem. I'm going to encourage you to go check out the notes for this one. It's all on there. I will guide you a little bit. You're trying to find the radius in inches of a sphere that has this mass. So I'm going to encourage you to go from your mass in ounces. We know ounces to pounds, pounds to grams. We know the density, grams to centimeter cubed. And then we can go centimeter cubed. Centimeter cubed you can get into inches cubed. So you're going to go to ounces, to pounds, to grams, to centimeter cubed with density, to inches cubed. Then we know that this is a sphere, so the volume of a sphere is 4/3 pi r cubed. So you'll know the volume, that's what you solve for here, and you solve for the radius. Your answer that you end up getting is 0.935 inches. In this last problem, we're looking at 1 grain of sand being a cube with this size. So we can find the volume of a grain of sand using that length cubed. I would encourage you to get into centimeters before you do that, so that way you can get centimeters cubed. Then what you can do is go from that volume in centimeters cubed. So, centimeter cubed. You can use the density to go into grams. And that will be how much mass 1 grain of sand. It's going to be a small amount. Then once you have that, that's the mass of a grain of sand. So you can find the number of sand particles by doing the total mass of the whole bag divided by the mass of 1 piece of sand. And that will tell you how many there are. And the answer is 3.2 times 10 to the 8th grains of sand. Okay, these are more realistic problems that you might face if you go into medicine or something like that. So if a nurse is required to start an IV drip at the rate of 18 units per kilogram per hour. The IV bag reads 25,000 units per 500 milliliters and the patient weighs 172 pounds. At what flow rate in milliliters per hour should we set it? So this is very familiar to me because I was in the hospital and nurses actually had to do this all the time to make sure I got the right stuff and it went in for the right amount of time. Okay, so we're going to start with this number that has a single unit, which is the weight. So 172 pounds. Okay, and we want to get to milliliters per hour. And you might be like, that's 2 units, what the hell? What do I do? Well, notice this one has like 3 units, so only one of those is going to cancel out, so we'll be left with the rest. That's okay. So we have a weight. We want to find something that has weight in it. And I'm going to say, okay, here we go, kilograms of body weight. So let's start with pounds to grams. We did that in another problem. We know that in 1 pound there is 453.6 grams. So now we're in grams. Now this whole unit has kilograms, so we're going to go all the way to kilograms. So there are 1,000 grams per kilogram. Now we're in kilograms. So now we could use this 18 unit situation. So I can now say I want kilograms to cancel out. And I have 18 units per kilogram per hour. So that means kilogram and hour are both on the bottom and 18 units is on top. Now we have hours, so that's good. That's what we want on bottom. We need to get rid of this unit kilogram situation. So nicely we have units right there. And actually kilograms are already gone, so cool. So we have units per hour. So we want to get to milliliters per hour, so we could use our last conversion, which is 25,000 units per 500 milliliters. Now I have milliliters per hour. It's everything I wanted and more. So then we have 28.1 milliliters need to be distributed every hour. Cool. Okay, last one of practice problems before the challenge. So we have a 298-pound patient requiring lidocaine at 30 micrograms per kilogram per minute, where blah, blah, blah. If you're supplied with a bag of lidocaine that reads 4 milligrams per milliliter, how many milliliters per hour? So, once again, the singular unit is our patient weight, so 298 pounds. We have microgram per kilogram per minute, so similar to up here. So we're going to go back into pounds, or out of pounds into grams, 453 grams per kilogram, or per pound. Then 1,000 grams per kilogram. Now we could use our, we want kilograms on bottom. That also comes with minutes down here. We can put our 30 micrograms here. Cool, so we are out of kilograms. We're into micrograms per minute. Now ultimately I want milliliters per hour. So I'm in a time unit on bottom at least, that's good. Okay, so I use this. Now I know that lidocaine reads 4 milligrams per milliliter. So I want to get, I want to use my milligrams to get out of micrograms. There are, there are 1,000 micrograms in 1 milligram. You could say that there are 10 to the 6 micrograms per gram and then 10 to the 3rd milligrams per gram, and do that. If you want to do 2 steps, then that's totally fine. Now we're in milligrams, so now we can use our lidocaine concentration there for 4 milligrams per 1 milliliter. I'm in milliliters per minute, so the last step is to get minutes into hours. So we have a minute on bottom, which means I need to cancel it out. I have to put it on top, and I want hours, so 60 minutes per 1 hour. Many steps. It is a tricky problem. Very, just a lot to think about and how to organize it. So if you didn't take this exact approach, it does not mean you're wrong. Hopefully you just got all the units to cancel out to get what you need, which is 60.8 milliliters per hour. In our very last problem, the challenge problem, although questionably the whole thing was challenging, especially at the end here, so bear with me. We have, so polluted air can have carbon monoxide levels of 15 parts per million, ppm. Average human inhales about 0.5 liters of air per breath, so that's a conversion, and takes about 20 breaths per minute. How many milligrams of carbon monoxide does the average person inhale in an 8-hour period? And then it gives us lots of conversions. So where do we start? So you might think ppm, that's a single unit, but no, that's a part per million, and as it says right here, it means 15 liters per million liters of air. So we can look at all of these different numbers and notice the only one that doesn't have a second unit is 8 hours. So we're going to start with 8 hours. And then we're going to try to find something related to time. So we have parts per million. We have that much air volume per breath. 20 breaths per minute. Hey, minutes. So there is our time. So we want to get our hours into minutes. So we have in 1 hour, 60 minutes. So now we're ready to use that. We want to get minutes on bottom. We take 20 breaths per minute. Okay, cool, done. Now we need to find something with breath. Oh, right before, we take a half liter of air for every breath. So we could say for every breath, take in a half liter of air. So now that one's done. Now we need to use liters of air. So we're ultimately, just to remind ourselves, trying to get milligrams of carbon monoxide. Right now we're in liters of air. Okay, so down here at the bottom it says for every million liters of air we have 15 liters of carbon monoxide. So we can use that. Million liters of air for every 15 liters of carbon monoxide. And then now we can use the density in liters of carbon monoxide. So we want to get liters on bottom. 1.2 grams of carbon monoxide. Get that bad boy into milligrams. So 1 gram has 1,000 milligrams. And we are done. So that gives us, in an 8-hour period of time, we inhale on average, if we're in this situation, 86 milligrams of carbon monoxide. Okay, so lastly, for reals this time, we have these different statements. They're all true. So we have Jessica's house is 5 kilometers from the grocery store. Jessica's house is 4.73 kilometers from the grocery store. And Jessica's house is 4.73927 kilometers. So what's different about these? I want you to think about it. Pause if you need to. Okay, so how can they all be true? So, and what does the number of digits have to do? So we know we have different sig figs here. And how does a sig fig change from measurement to measurement? That will be the number of tools, or the precision of the tool. So basically what's happening here is our tool is getting more precise. Maybe this is just her estimation. It's about 5 kilometers. Maybe she uses a GPS. There, maybe that tells her. Maybe she uses a pedometer or a watch, a smartwatch to get her there. It gets her more. So every statement can be true. It just depends on the instrument we're using to measure. So, way to go. You made it through Chapter E. This end part was kind of a long haul, and I hope the homework, it shouldn't be as intensive as the amount of problems, but I want to give you lots of opportunities to practice because this is something you need to be kind of really not good at doing, but good at, comfortable with doing, because we're going to do a lot of conversions.